So here we go on the final section of topic 17, and this links Gibbs free energy and equilibrium. And you may recall that we did look at this very briefly at the end of when we were doing Gibbs free energy. Key point here is to remember that a reaction is spontaneous from left to right if delta G is negative or becomes negative. Because if you read the sentence, you'll see that the Gibbs free energy changes during a reaction as the reactants become products. I wouldn't worry too much about the graph. It's possibly a little bit confusing, but remember the key point that for a spontaneous reaction, then delta G becomes more negative. Now there's an equation that links delta G and Kc, and you can read that as well as I can. Delta G standard is minus RT natural log of the equilibrium constant. Now the natural log, if you're not a mathematician, you don't need to worry about what it actually is, but it's just a button on your calculator. So to convert Kc to natural log of Kc, you simply press the button on your calculator. Okay, R you're familiar with. T will be the temperature in kelvins, which if we're talking about standard conditions, which we usually are here, is 298 K. We've seen something like these statements before. When Kc is large, delta G is going to be negative, and when Kc is small, the reactants are favoured. The natural log is less than 1, and so delta G will be positive. Now, this final paragraph is one of the most important parts of this little section. The position of equilibrium corresponds to a maximum value of entropy and a minimum in the value of Gibbs free energy. And at equilibrium, therefore, delta G is equal to 0. Okay, if you remember nothing else from just now, then remember that equation from the previous slide and that little statement there. Here is exact repetition of the slide that I put in topic 15. Okay, you can read that as well as I can, but hopefully the numbers will mean a little bit more to you now for Kc. Remember, the double arrow or double chevron means much less than or much greater than. So what sort of things do we have to do with the equation? By the way, the equation is given in your data book. Well, the most likely thing is that you'll have to calculate natural log of Kc, or therefore Kc, from delta G. Or I suppose vice versa, but then that's easy peasy, just plug it into the formula. So there's the rearranged version of the formula. So here's a for instance. Calculate the value of the equilibrium constant Kc at 300 K for the reaction as shown. You've got a value for delta G given there, and I've asked you to think carefully about the units. So please plug that in, and I'm looking at my answer with a degree of suspicion here. First time round I've got that as 298 as the value for natural log of Kc. Now, how do you then go about converting that to Kc? Well, it depends on your calculator. On many calculators, it is shift ln, and that will give you the correct value. Some calculators will get sulky with that sort of value for Kc, 2.6 times 10 to the 129. They don't like it, but I've managed to get it on my scientific calculator. If you're struggling to convert, then don't worry, I'll try and sort it out for your calculator if you tell me your sort of calculator. But do have a play. It does depend on what sort of logic your calculator works. Different calculators work in slightly different ways. But have a fiddle with 298 and the natural log button, or it might be just e to the 298. It might be what you need to do. Depends on your calculator. But have a go and see what you get. Here's a second example for you. Because we're involving a reaction here with gases, it's actually quite difficult to measure Kc. The actual concentrations are difficult to find, so it is more often calculated using delta G. And this might be something you could consider for an IA, comparison of values from delta G calculations for Kc with lab calculations. So you can read the question as well as I can. I don't know why I've written delta G twice, but never mind, I'll get over it. And I want you to use the equation to calculate Kc again. I get that as my answer. Okay, again, check through, and if you're unsure how to work the logic of your calculator, then it's either going to be e to the value you got for ln Kc or shift log. Most will be shift inverse log. Oh, sorry, inverse log or shift log. So you should get a large, or you have got a large positive delta G, which gives you a very small Kc. What does that tell you about the equilibrium mixture? Well, it doesn't take a genius to work out that, of course, the equilibrium lies very much to the reactant side. Hardly any reaction has occurred. So that is actually now the end of topic 17. The next thing for us to look at will be to start the higher level for topic 6, so topic 16, and I will post the presentation on Google Classroom in the next 10 minutes or so.